A biologist of all time, Robert Schreibers, who applied mathematics in a trivial mathematics in a highly non-trivial way. And I'm going to hear about it.
Actually, I left some feature of my talk somewhere, but it's on this computer if it'll turn on. Okay, this is going to be real simple. And there's two reasons for that. The first, as I used to joke when I got into this field 35 years ago, evolutionary theory was so poorly developed as a discipline that fractions and logic would get you through most situations. And I'm afraid we're not a hell of a lot further along than that. Fractions and logic will still get you through most situations. There's been some progress in some limited areas, but mostly we suffer from what a number of disciplines suffer from when math first gets introduced. That is, those with slight mathematical talents dress up their papers with equations so as to look more complicated and more scientific. In other words, they use it as a device of self-promotion and camouflage. And there's no content specifically in the math. Indeed, content is usually hidden from view. And another thing that happens, and economics provides, if not endless, at least numerous examples of this, is they will solve something in economics that was already solved in physics like 400 years before. And yet, because it's in a novel context, they will pretend to give it new meaning, but in doing so, they have to make elementary mistakes in logic. So certainly as mathematicians, we all, and I'll pretend for the next hour I'm one of you, we all know that mistakes at the foundation are the most important and far-ranging. To give you just one little example of this game economists have played, this was an argument I had with Paul Samuelson years ago, just after he got his Nobel Prize, which he then paraded around everywhere he went, as you might expect. So he got in an argument with me about sex ratio theory. Now, sex ratio theory could not be simpler. If a male and a female cost the same to produce, then 1-to-1 sex ratio at hatching, or when they're produced, is the ESS. It's the equilibrial stable strategy, which cannot be displaced by anything else. And it's easy enough to see why. If everyone's producing 1 to 3, then a male's reproductive success is expected to equal 3 times a female's reproductive success. And therefore, a parent is now selected to produce sons instead of daughters in order to get these extra grandchildren. And of course, it's just the other way around if it's 3-to-1. Now a male's RS is 1/3 that of a female, and parents are selected to produce the underrepresented sex. So natural selection acting on individual parents favors them producing a 1-to-1 sex ratio, or slightly more accurately, favors everyone producing sex ratios that will average out to 1-to-1, at which point there's no particular bias in favor of any sex ratio. So what does Paul Samuelson do? Paul Samuelson reproves the notion that if you have 50 red balls and 50 blue balls in some big space bouncing around at random, then you maximize, well, if you have 100 that can be either red or blue, I should have said, you maximize the chance that a red and a blue will collide if there's 50 of each. If there's only 1 red and 99 blue, that red will always collide with a blue, but almost all the rest of the blues, 98 of them on that instance, will collide with each other. So it's absolutely trivial that to maximize collision rate, 1-to-1 is the optimal sex ratio, or optimal ratio of balls. It has nothing to do with natural selection acting on the sex ratio. Natural selection is not trying to optimize collision rates of males and females in nature. That's a group characteristic, not an individual characteristic, and the classic corrosive assumption in evolutionary theory ever since Darwin, and we're still trying to beat it out wherever it pops up again, is that evolution evolves at some higher level than the individual and or his or her genes. The group, the species, the ecosystem, the universe, if you really want to lose all moorings to reality. Okay, so let's deal with fractions now and kinship theory. Now, kinship theory is the only important advance in our understanding of evolution since Darwin. Darwin said there's variance in reproductive success in every species. Some individuals produce many surviving offspring, many fewer none. By definition and logic, the genes of those producing many become more numerous. The genes of those producing fewer none become less numerous. That's the end of the subject. So all we have to do to understand life is understand how natural selection has worked on our traits and imaginary other traits for many, many millions of years. Now, by logic, though, we're not only related to our children. So it was Hamilton's advance in 1964 to extend this system and say, wait a second, you're equally related to your full sieves, your brothers and your sisters, under outbreeding this is, as you are to your own children. So in principle, natural selection can favor you having no surviving offspring if by doing so you add more brothers and sisters to the world than children you would have had. Okay? So he adopted an extended reproductive success or extended genetic success, where you still were maximizing a single number, that is your number of surviving offspring, plus your effects on relatives' reproductive success, with each effect being devalued by the relevant degree of relatedness. So as I mentioned, if you're considering an effect on a full sibling, you have to devalue the effect by a half compared to the same effect on yourself, because you're fully related to self, half related to future sibling. Fine. So that's the foundation for all of evolutionary logic. It ain't been changed since then. And that's where fractions come in. Now, how exactly do we define degree of relatedness? That's all I want to talk about now for the next 10, 15 minutes. How do we define it? What difference do slight differences in our definition make? So here's a recent paper published in either Nature or Science by Martin Nowak, who apparently reserves space in those journals because every 3 months there's another new paper that's coming out. And this one was particularly full of nonsense regarding the evolution of youth sociology, and it created a whole Sturm und Drang. Anyway, let's just look at his definition of R, or what I call degree of relatedness, and I'll define it in a moment. But he defined it as the fraction of the genes shared by the altruist and the recipient due to their common descent. I would not define it that way. I would define it as a conditional probability. If I have a gene, what is the probability, given that I have it, that this gentleman here has an identical copy of the gene by descent from a common ancestor? This is slightly different. And this reminds me of a brief little quasi-literature that grew up and unfortunately died very quickly, when people took the fraction approach instead of the conditional probability approach. So, for example, there were some people that said, look, we're all, as parents, we're related to each child by a half, period. Because if meiosis is working properly, it's always taking one of the parental chromosomes or one of the sections of the parental chromosomes and sticking them in one sperm cell or egg and the other in another one, and it's doing this exactly 50-50, because that's how meiosis works. So there's no variance in degree of relatedness as you look at your children. It's all half, 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 half. Of course, there may be variance in the ability of your children to convert investment in them into grandchildren. That's another matter. But they then continued and said, but there is variance in the fraction of your genes that are shared with a sibling. Because here you have independent assortment going on, and you can have slightly more than 50% of your genes in a sibling, or slightly less than 50% in the sibling. The fact that you have 23 independently assorting chromosomes, and in fact crossing over within them that virtually doubles the number of chromosomes, means that those deviations are pretty damn small. But nevertheless, it was big enough for some people to say, we expect siblings to differentiate among themselves according to how related they really are. Try to beat this conditional probability by actual knowledge of how many of your genes happen to be shared by chance with a sibling, even though the chance for any given one is a half. The problem with that is that you still have to imagine a gene that decides to make this measurement. And this gene is going to be found in the other individual with a chance of a half. The information about other genes that happen to have gotten by chance assorted to this sibling more or less frequently than 50-50 is irrelevant to what's happening at this locus that you're imagining is making the measurement. So we thought that that was probably a false lead, really going nowhere. Now, okay. Now there's a larger problem of identity by descent. Why is that our criteria? Why did we say degree of relatedness is a conditional probability that you have a gene that I have by descent from a common ancestor? Why don't we just talk about the chance that you have that gene, period? Well, that led to a whole blossoming theory that died after 8 or 10 years, painlessly, I imagine, or never mind the pain in it. That was called genetic similarity theory. So that's back to the sibling fallacy, only that's writ up large for our genotype itself, and that says, hey, look, I've already sharing most of my genes with you all because we're human beings. So degree of relatedness already starts at 0.9, if you will. But that is foolish on the face of it. Again, when you imagine that a mutation appears to act altruistically toward a given category of individual, like a half-sibling, then it is irrelevant that it appeared in a species where individuals already share 95% of their genes in common because they have 2 legs, 2 arms, 2 eyes, and a whole series of other things in common. Okay, you say, I'll go along with that, but what about at the locus itself? What about at the locus controlling your imaginary altruistic act? Surely, when you first have the gene pop up, you can talk about identity by descent from a direct ancestor. Actually, there's a slight delay before you can. When it first pops up, it won't be found in a sibling. It has to pop up and 2 or 3 generations go by before it shows that kinship structure. But give us that. Then it starts at a low frequency. Now it's being favored. Whenever benefit times R is greater than C, which for the full SIB case would be whenever the benefit is greater than twice the cost, the gene will start to spread by logic. Okay, fine. Now, as it spreads at that locus, it is no longer found there infrequently. Indeed, it may reach 50% frequency, or it may reach 99% frequency. Surely, if it's reached 50% frequency, then the conditions for its further spread should be relaxed because it has achieved a frequency already. No. Once again, that turns out to be a logical error, and one way to conceptualize it, I think, is a simple drawing that's meant to refer to one locus. A locus is a location along paired chromosomes, and so we have where there's typically a gene or an allele at each of the places on this chromosome. So here's a locus, and it's a locus that affects how you act towards your full sibling, let's say. Now, you've got the gene, okay, by definition or by assumption, because you're an altruist in this situation. Now, what about the paired one here? Well, let's say that it has reached 30% frequency, but as we all know, we can make this general. So we'll simply say its frequency is P, that it's present, and 1 minus P, it's absent. Okay? Now let's look at the recipient, the other individual. We'll make this the full sieve. Okay, the full sieve, by descent from a common ancestor, identical by descent from a common ancestor, has half the gene, or has the gene half the time. Now the rest of it is going to be made up of our good old P's and Q's. P, Q, P, Q. So natural selection, striking this part of your loci or genome and that part, cannot change gene frequencies because it hits the genes in the frequency with which they already exist. So a third of the time it gets a benefit, let's say, or let's say here, a third of the time it suffers a cost, because you're suffering a cost to transfer a benefit if it's an altruistic act. You know, a third of the time it gets a benefit, but 2/3 of the time its alternative gets the benefit, and that's the ratio at which they're found. So by simple logic, the frequency with which the allele has, the frequency the allele has achieved does not change the direction of selection. It still remains the case that it is only the correlated portion of the genome, as we like to call it, that determines the direction of selection. The fact that you definitely have a gene, and the fact that putatively your brother or sister has it half the time. The only difference, the only effect of this section of the genome is that it will slow down selection. Let us say, for example, that you're dealing with behavior toward a cousin, then this is only a quarter of this is only occurring an eighth of the time, sorry. And so it's smaller, which means the uncorrelated section is bigger, which means that the forward selection of this gene is slower because you're wasting more of the time taking the red and blue balls out of this box at random, increasing them or decreasing them and flinging them back in. Okay, fine. Now, how far have we gotten? Okay. Now, is there this possibility? Is it possible now for a gene to recognize itself and confer a benefit directly on itself? Or does it just have to rely on indirect evidence that the other individual has the gene because of descent? So this was popularized by Dawkins with the name green beard, because it was a gene that gave you a green beard and then gave you the impulse to like individuals with green beards and to transfer benefits to them. So it's a green beard gene that recognizes itself phenotypically in someone else and transfers the benefit. Now, you may have noticed that green beards are infrequent. And indeed, this kind of gene is very, very infrequent. I will mention one kind that's kind of a special category, but we've had cases that people have pushed forward, and maybe one or two have survived critical scrutiny, but that's about it. It's a very, very small category. And the reason we believe that's true is that the rest of the genome ain't going to be happy with it. If I've got a green beard gene that gives you a benefit just because you got a green beard, all the rest of the genes in me that are not linked to this green beard gene are not going to be happy with my wasted investment in you, because they don't share any resemblance to you. So a critical feature of kinship is indeed the fact that it tends to work across our genome. Not completely. And that's a whole separate world, which I'll touch on in 1 second. But in general, across all our autosomes, if I'm half related to you at this locus, I'm half related to you at every other locus. So they're all in agreement that we're going to act nice whenever B is greater than 2C. So in other genes in you are going to be busily selected to shut down green beards if and when they appear. There are some exceptions to this, and let me just mention one. And, you know, does anybody have a watch they would consider lending me? Thank you, brother, because, you know, I hear Doran can get pretty ugly towards the end of this. So what is the end? When am I supposed to shut up?
It's 5:45.
5 what?
5:45.
5:45?
So
Jesus
people have
Christ,
10
Doran, I better
questions.
pick up the speed of this.
If you have, or 5:50 if you want no questions.
Okay, thanks for that choice. So, one example are cell adhesion molecules that are homophilic and operate in human pregnancy. So basically you've got a cell, and then you've got a molecule here, and this has some shape in here. And it connects with, let's make this thing out like this, and let's just say that it chemically bonds with the same damn molecule in the mother, which also has its structure down here for what it's supposed to do. So this is mother, this is offspring. And it will, if there's a match, tend to suck resources from mom. And the interesting case turns out to be when she's heterozygous, so that some of the offspring have the gene that's going to hook up and some don't. But the point is that within the individual, I'm completely happy with this homophilic gene getting more resources from mom that are going to other fetuses, as long as it's not too great. You know, as long as the costing isn't twice the benefit if we're full siblings. So there can be circumstances that then spread through to fixation, and then afterwards you don't even think of it as a green beard effect that went to fixation. You just think of it as mother-offspring coadaptation at the placental boundary. Okay. Now, this I cannot state for you well, and my apologies for it. People who are mathematically talented claim that kinship can be restated in terms of group selection, and the statements, if done properly, are isomorphic. Group selection, when done properly, talks about within group variants and between group variants in genetic traits, and compares the two. And then it has to have rules regarding the formation of new groups and blah, blah, blah. I call a friend of mine who's an expert in kinship theory, and I say, look, when you apply this to just two individuals, you and me, who's the group here, and how do these group people do it? Because I don't bother thinking about kinship in terms of something more difficult, group selection, than simple kinship theory, simple probability. And he said, and I don't know whether this is true, that he thought, because he's like me, he thinks in this system and not the group selection one, that they set up systems where the group of him and me actually consists of different alternative individuals that may both have the allele, may have one allele and the non-allele, and have neither allele, and then you have the combinations with the other three individuals, and you somehow work out all that, and you come up with B greater than 2C for full siblings, let's say. Then all I want to say is, and you people must know this much more deeply than I do, just because two languages are isomorphic or can be made isomorphic does not mean that they're equally useful in thinking about things. And the simple approach to kinship theory that I've tried to give you can lead you quickly into seeing novel things which, if you had to formulate them originally in terms of group selection, you still wouldn't see them. And I just give you one example. Because when people argue this group selection stuff with me, I say, fine, how many centuries would it have taken you to think up genomic imprinting? Yet the logic was thought up very, very quickly based on simple kinship theory. What is genomic imprinting? Well, let's look at your degree of relatedness to your half-sibling related through your mother. And we start with you always, and we want to know what the chance is, identical copy, in your half-sib. And so degree of relatedness equals a half times a half equals a quarter. Now that is with complete ignorance. Ignorance, i.e. the gene here does not know where it came from. Now let's give it knowledge, or complete knowledge, exact knowledge, any way you want to word it. Now we have a situation where we could have a maternally active gene that knows it came from mom, so to speak. It is related to mom by 1, and there's a half chance she passed it down. Sorry, this is so ugly. And so therefore, degree of relatedness for a maternally active gene equals a half. Or it could be a paternally active gene, in which case we know it didn't come from mom, and 0 times a half is 0. So, R for a paternally active gene equals 0. And you can think of the quarter as being the average of these two, or as genomic imprinting permitting you to segregate 1/4 into a half and a 0. Now, I said paternally active or maternally active, and that's precisely the mechanism of memory that has evolved. That is, we now believe that there's up to 5% of our genome consists of genes which are, the copy from one parent is active, the copy from the other parent is inactive. So you have paternally active genes where the identical genetic structure, the identical base pair structure, if coming from mom, would have been turned off, silenced. And that's why they call it genomic imprinting, because there's some imprint put on the genes during oogenesis and spermiogenesis that turns them on or turns them off, independent of their DNA structure. And likewise, you can have the reverse. So whether the gene knows anything about this or not is all irrelevant. The point is a paternally active gene can act as if it is sure that if it is active, it did not come from mom. A paternally active gene, put a different way, had to come from father. It could not come from mother, and the same thing's reversed for maternally active. Well, as I say, I'm just using that as an example. That's, by the way, a fascinating and extremely important area. And when I told you earlier that it wasn't quite true when I was using this man as an example of degree of relatedness of a half, I said it's across all our autosomes. Well, the X and the Y, it's different. Mitochondrial DNA is different. But now we know our maternal and our paternal genes see the world differently. And that's half our genome against the other half. And it has very important effects early in life, but now we know it has effects all throughout life, in the life of mice, humans, and some other creatures. Okay. Well, good. That leaves us next to no time for reciprocal altruism. So let me just talk about reciprocal altruism briefly. So my first paper was on reciprocal altruism because Hamilton had come out with kinship theory. And yet it was obvious to me, just looking around the room, that there are people that are friends of yours to whom you are negligibly related, yet to whom you may have warmer feelings than you have towards some, or indeed many of your relatives. You may have heard the folk expression, you get to choose your friends, you're stuck with your relatives. And that's one reason why we can feel real close to a friend. So I said, well, let's try to model this. Let's try to model altruism and good feelings and blah, blah, blah between individuals to whom relatedness is not the key. And so the notion was very simple, reciprocal altruism. If you scratch my back, I'll scratch yours, but with a time delay. If we're scratching each other's back simultaneously, we can adjust things so that nobody's getting cheated too bad. But if you do something nice for me and you got to wait 2 weeks for the return benefit, and then, you know, do I remember? Am I around? Do I give you as much as you gave me? Blah, blah, blah. So you have the problem of the cheater. And the cheater, in turn, comes in two forms. A gross cheater who doesn't reciprocate at all, that's easy to discriminate against. And the much harder one is someone that reciprocates, but not quite as much as you would if the shoe were on the other foot. Out of that, I thought, came, yes, feelings like friendship and so on, but also eventually a sense of justice. I don't think kinship selects for a sense of fairness. I'm selected to act nicely towards relatives and to be concerned about their misbehavior and so on grounds of degrees of relatedness. And fairness doesn't obviously come into it, but fairness surely comes into reciprocal relations. So I thought it was also important eventually for a biological understanding of justice. Okay, now, I got a letter from Robert Axelrod, who's a political scientist, and he was going to play iterated games of Prisoner's Dilemma. Everybody heard of the Prisoner's Dilemma in here? Okay, nobody fessing up otherwise. But the Prisoner's Dilemma is a simple game where you either cooperate or defect. If both of us cooperate, let's say both of us get 3. If one cooperates, I'm the fool, and you defect, then I get 0, but you get the benefit of having fooled me, so to speak. If we both defect, then let's say we both get 1. I think this has the proper structure of a prisoner's dilemma. In a single game, we should both go to D, because I'm better off with D if you have C, and I'm better off with D if you do D. So in both cases, I should prefer D, you should reason the same way, we both end up here, and we both forego this. But in iterated games of Prisoner's Dilemma, you can imagine that we might come up with some way to cooperate. Now, there's a mathematical argument that it's not just iterated games, but there must be uncertainty about the end of the iteration. If you know that the game is going to be played 100 times, then you know on the last move you're going to defect. And then because you're going to defect on the last move, you're going to defect on the second to last. And you argue backwards, okay, at least logically. So they added this uncertainty regarding the ending of the game. Now then, the letter said that he was sending this out to a lot of people and asking them to devise a strategy that could win iterated Prisoner's Dilemma. He asked that it be a computer program if possible. I didn't even know how to turn a computer on back then. And I made one big mistake. I thought it was going to be complicated. I thought that you would like to remember back past one move or two. You would like to adjust your behavior to the fact that Doran is now a 70% cooperator, and therefore how should it affect me? And that was a big mistake on my part. And I don't know about the rest of you, but I like to remember my mistakes. I like to sit up and notice. And I sure sat up and noticed here because in came his results, and Anatole Rappaport, who was a game theorist, came up with the simplest strategy. Well, the simplest is always defect. That doesn't give you much. It's a lonely world. You cannot be driven easily out of it. You're all by yourself. Always cooperate is easily driven out by always defect. But tit for tat was the simplest beyond these, and it succeeded. It beat every other strategy put in. So the rule for tit for tat was cooperate on first move and then imitate partner thereafter. Okay? So you start out hopeful in life, and then if the other one's defector, then I'll be a defector towards them. If they're a cooperator, I'll keep cooperating. Okay. So, two things were important to me right away. First of all, it was a damn simple rule, and the virtue of that, to someone like myself who likes to see principles in social theory applied as broadly as possible, it can apply to bacteria. You can be a bacterial cell, you put a compound out into the water, which is beneficial to you, but also beneficial to the neighbor. And you have a detector as to whether you're getting back any compound from the neighbor. And if you're not, and the cost-benefit works out that that don't make no sense, you stop producing the beneficial chemical. If the individual puts out the beneficial chemical, so the two of you now are swimming in sufficient beneficial chemical to make it worthwhile, you keep it up. So you do not need this complex machinery of remembering, well, yeah, what did Doran do to me that day? Yeah, well, why did he stiff me there? And that was a pretty ugly thing he said in the faculty meeting, and blah, blah. We'll add it up and remember costs and benefits going back and somehow extract a strategy. No. One move into the past only, and you could get a workable system. Second thing, by the way, it suggested a novel function for imitation, because I'd always thought of imitation as some kind of learning mechanism, but here you can see that some imitation in us, and it is true in certain aggressive situations that someone will say F you and you'll say F you too. So it's like there's a kind of immediate imitation of behavior that fulfills the tit-for-tat role. Okay. They then showed, Axelrod and Hamilton then showed in a paper that this was an ESS. If you gave it a little help at the beginning. When it's very rare, it's hard to get it going. So you've somehow got to get it going in a king group or going for some reason. And then it'll start to take off. And it'll be an ESS, which cannot be forced out of the game, the well-defined game in which you put it in the first place. So let me just mention a couple of other things that have been done since then. If I can find it. Okay. Now, just two things they've done since then. First of all, they added mistakes. And there's lots of reasons why we make mistakes in life. So if you add mistakes, then tit-for-tatters can be put into a bad situation, where you and I are both tit-for-tatters, but for some reason I defected. And so we now imitate each other. And so we spin through evolutionary, or not even evolutionary space, just our life space, always out of phase with each other. We're two tit-for-tatters, but we're losing all the time. Okay? So this can be protected against by a strategy called generous tit-for-tat, or forgiving tit-for-tat. And it says, cooperate on the first move, cooperate on all successive moves if your partner does, but for the defection, every third time you're supposed to defect, cooperate instead, as if you're forgiving them. And that then gets you out of this bind, because you go through a few of these and then suddenly you reverse, and now you're back in glory land together. CC all the way down. Okay, fine. Now, a new game thrives in a world of tit-for-tatters, and it's called win, stay, lose, shift. And so if you win, if you got a good reaction from your move, stay with it. So that means if you defect and the other cooperated, keep with that strategy. Okay? You don't switch to C because the other one did C. You stay with D because that's working just fine for you. But if you lose via D, let's say, then you shift to C. So it's win, stay, lose, shift. And it protects against exploitation, it corrects errors, and it exploits naive cooperators. Those are individuals who just cooperate no matter what, because you'll eat them alive here. It cannot get going in a world where there's many just plain all D individuals. But if the latter have been driven out by the other two, tit-for-tat and generous tit-for-tat, then all C, cooperate all the time, will spread by drift. That's easy enough to show. And then win, stay, lose, shift starts to take off, partly because it's sucking out benefits from all C. Okay. A benefit of all this is that you can do experimental games on it, and so you can mimic the game theory with games that people play in the lab. And sometimes those are very interesting. So we know, for example, the generous tit-for-tat is less cognitively demanding, and that, well, you can prove that, 6 ways to Sunday, then win, stay, lose, shift. And sure enough, when extra cognitive demands are made on people in experiments, like they have to do a memory task every other set of tit-for-tat games they play, they shift more towards the cognitively less demanding one. And if they don't, they start doing more poorly on the memory test. Enough. Now I want to turn to deceit and self-deception. And I've got 5.5 minutes with 3.5 minutes left for question. I just, let's see, did this computer ever turn on? Yeah. Well, hell, maybe I'll even remember it. So I've just finished a book, finally, on deceit and self-deception, and the key problem is, why do we lie to ourselves? Lying to the rest of you is no problem at all. But lying to myself, where the hell is the payoff in that? And my basic argument is that it improves my ability to lie to you, and I've organized a world of information around that hypothesis. Now, what about some mathematics on the subject? Obviously, if the better we had mathematics on deception, that would help our theory of self-deception, because it depends on our logic regarding deception. But the logic that's been advanced is either trivial or wrong. Trivial is that the game tends to be frequency dependent. When deceivers are rare, they do well. When deceivers are common, they run into problems. They run into each other all the time, and people are aware of their deception, and so it's frequency dependent. And that'll sometimes lock the roles into an equilibrium where neither is driven extinct. Fine. Then that's trivial. Now, false logic was the logic that this selection for spotting deception inevitably increases the cost of the deceptive apparatus until the organism can't maintain it, so that truth wins in the end because it drives deception out, because it makes deception more and more costly. Now the model for this is, why don't we have deer running around with paper mache antlers that really didn't cost them much, but have all the ability to fool and impress. And so the argument is, well, you had female choice and male-male aggression on top of it, grinding out to give an honest signal of quality. The only application of this logic that even half works is courtship signals. They will tend to become more expensive over time. But there's no general logic by which deception should be replaced by honesty. But this is a very deep feature of our psyche, apparently. I'm speaking the species now, that we like these damn arguments at the level of the group, or where we end up saying, everything's working out fine, give it time. Selection favors honesty, just through cost, just relax. It ain't true. Now, what about applying this then to this game theory to deceit and self-deception? Well, a prisoner's dilemma won't work, because if you defect on me, in other words, I tell the truth and you lie, the most appropriate response is usually not for me to tell a lie back to you. It's usually for me to distance myself from you, have less interactions with you, perhaps punish you for the lie, but not mimic you, not lie back. So I don't see any hope for prisoner's dilemma being used to model the evolution of deception. But Carl Sigmund, a mathematician in Vienna, came up with a very clever notion, and he used the ultimatum game. Have any of you heard of that, the ultimatum game? Here's how the ultimatum game works. Someone else, at the University of Zurich, puts up $100 and gives it to me as the proposer, and I propose a split to you. And the split I propose is I'm going to keep 50 and you're going to get 50, and you get to say yes or no. If yes, we each get $50. If no, we leave the lab with nothing. And that's how it's played. Okay, so you're going to say yes, of course. But you're going to say yes for 60-40 also. You're not going to give up $40 just because I took 60. But at what point can I drive you down to the thing where you say, F you too, I don't care. And it's 80-20 is when half the people bail out. So I loved the work when I first heard about it because it was a way of measuring our sense of injustice, because you had to pay for it. So, that my sense of injustice kicks in at 80-20, and then I'm willing to pay the $20 cost to inflict the cost on you. So there's a whole nonsense literature on what's it called, strong reciprocity, which I'll skip, where again they try to show that all this is for the good of the species. But anyway, Carl, geez, now, this, I was going to check on, you see, so that I don't want to misrepresent old Carl. Okay, where is Carl here? So Carl proposed a special kind of version of this damn game, and you guys can start asking questions if you want.
What did Carl propose?
What's that?
What did Carl propose?
What's that?
What did Carl propose?
Well, wonderful question. I love you, Doran. Let me see if I can answer. What the hell did Carl propose? Okay. Now imagine a modified ultimatum game in which there are two possible pots, say $100 and $400, and both players know this. Okay? One pot is then randomly assigned to the proposer. So let's say Doran has $100, but I don't know whether he's got 100 or 400. Imagine Doran offers you 40. This could represent 40% of a $100 pot, in which case you should accept, or would be expected to accept. Or 10% of a $400 pot, most people would reject. Okay? Then, he has an unusual step in here that maybe you mathematicians can explain. I mean, it's clever, but I'm not sure I understand it. The proposer is permitted to lie and tell you that the pot is smaller of the two when in fact it is the larger. You can trust the proposer or not, but the key is that you are permitted to pay to find out the truth from a disinterested third party. So I guess I ask you, or Doran it is, and he lies and says it's 400, although that would not be to his advantage so much. It would be the other way around. You'd expect him to lie. And then I can pay now to find out if he's told the truth. This measures the value you place in reducing your uncertainty regarding the proposer's honesty. If you then discover that the proposer lied, you should have a moral or at least moralistic motive to reject the offer, and the other way around for the truth, all compared to uncertainty, i.e. not finding out. Note that from a purely economic point of view, there is no benefit in finding out the truth, since it costs money, after which it may lead to an otherwise unnecessary loss of whatever is offered. The question can then be posed: how much would a respondent be prepared to pay for reducing the uncertainty and go for a possibly inconvenient truth? Note that the game can be played in real life with varying degrees of anonymity and also multiple time, as in the iterated prisoner's dilemma. An ability to discriminate develops, the other person will benefit more from your honesty, quickly seen as such, and suffer less from deception, spotted and discarded. When you add self-deception, it becomes even more complex. I left 1 minute for questions. In the name of Doran Zeilberger and everything that we mathematicians have regard as holy, I give you 1 minute.
Thank you for a great talk. We have 2 minutes for public questions, and Robert will be glad to answer questions in private after these 2 minutes. Any public questions?
So as you prepared for this book, they observed patterns of deception in chimpanzees, front of the ball down, Yerkes. Does that play into your model as well? I mean, have you compared to other species besides humans and how they behave?
Well,
does it fit within them?
Yeah, there's no comparison of two species, but I'll mention something that goes across all monkeys and apes, and I believe is a general rule, and it's one that I think most of us intellectuals would be surprised at initially and maybe averse to. And that is that if you look at the size of the neocortex, the social brain, or just the size of the brain itself, corrected for body size, across all primates, monkeys and apes, ourselves excluded, here's the relationship between how often they're seen practicing deception in nature and how the relative size of the neocortex. So the smarter you are as a monkey or an ape, the more you lie, not the less. Now children, same thing is true. 4-year-old children, they're put in the following situation where there's a box behind them and the experimenter, and they're sitting there, and the experimenter puts something in the box and shuts it and says, now don't peek, don't look in the box. And then they leave the room and of course watch. Now, most children peek. Then they come in and say, did you peek? And most children lie and say they did not peek. But the tendency to lie, again, maps on a simple, crude kind of cognitive ability test, so that if you've got a bright child, 120, they lie 100% of the time. If you've got a slow child, they lie 65% of the time. So contrary to what we might like to believe and imagine is true, I think higher intelligence is associated with more lying and probably with more self-deception. Certainly, certainly probably more sophisticated forms of self-deception, you know. And I think people that are smart and lie tend to have to deny the lying to themselves, and so they're going to practice self-deception right along with it. Anyway, so I've looked at an awful lot of creatures and various kinds of human data, but that's an example of data from other creatures and humans.
Let's thank Robert again. I will be very happy to answer